Thanks, Ronald, for the introduction. So this talk is on memory sample lower bounds for learning with classical and quantum hybrid memory, and it is a joint work with Qipeng Liu and Raz. And I'd like to give special thanks to Uma Girish for extensively participating in our discussion. So let's start with a classic example for this learning task, the parity learning problem. So in the parity learning problem, we have an unknown n-bit string x, and the samples we are given are in the form of A and B, where A is a uniformly n-bit string and B is the inner product of X and A under F2. And in the classical model, to bound the space and time for this learning task, we use layer branching programs. So these are the directed acyclic graphs that have their vertices arranged in layers. And you start in the initial vertex, and in each step, you branch out according to the sample that you received. So for each vertex not in the last layer, there are two n outgoing edges labeled by the possible 2 times 2 to the n outgoing edges labeled by the 2 times 2 to the n possible samples that you receive in each step. And in the last layer, each vertex needs to output its guess of what is the correct x is. So the time is the length of the branching program, so it's the number of layers, and the space is logarithmic of the width of the branching program, which is the number of the vertices in each layer. So Raz proved in 2016 that for parity learning, you either need quadratic space, where you can just remember like n linearly independent samples and apply something like Gaussian elimination to find out x, or you need exponentially many samples where you just wait for the best samples that you can get each bit of x directly. Right? So you either need quadratic space or exponential time. So a natural question to ask is that what happens if we have the power of quantum computing? Can we solve this problem much more efficiently? So with quantum computing, we need to modify the model into a quantum branching program. So in a quantum branching program now, in each layer, it is not like a discrete distribution over these vertices. Instead, you have a superposition over these vertices. So we can just think of it as a Hilbert space of dimension 2 to the s, where s is still the space usage of the branching program. So you have s qubits, and in each layer you have a quantum state in this Hilbert space. And you start off with a fixed initial state, and in each step, instead of just branching out, now you just apply an arbitrary quantum channel on the state that you have, where this channel is controlled by the sample that you received. So if you receive the sample A and B, you apply a channel with subscript A and B, and you just evolve this quantum state until the end. And until the end, you apply a general measurement, like a POVM, to output your guess of x. And this is the model where we are using. So the question now is that if with this model, can we do much better than the classical memory and sample lower bound? So is there a quantum learning algorithm within this model that solves parity learning with, say, subquadratic space and simultaneously have, say, polynomial time? So this question is actually a win-win question. So either answer to this question will give you some kind of breakthrough or like a good subsequences. So for example, if the answer is yes, then we get the first unconditional exponential separation between classical and quantum learning with a bounded space for classical learning problems. So I stress classical learning problems because this separation is already known for intrinsically quantum learning problems. So in those problems, the samples are actually quantum states. So it is kind of natural that classical learning algorithm cannot have an advantage on this kind of problems. But it is still open for a classical learning problem that is purely classical. And on the other hand, the problems like parity learning is a kind of a natural candidate, because these kind of separations are actually very hard to prove. That we show in the previous work, we show that if we prove such a separation in the regime that the quantum learning algorithm has spaced logarithmic in time, then that actually implies a much stronger separation for decision problems. That BQL, so it's a quantum log space, is not equal to BPL. But for parity learning problems, what we are shooting for is something like a quantum learning algorithm that, say, use linear space and polynomial time. So it does not fall in this regime. So it does not have such a barrier. And on the opposite side, if the answer is no, then first we have a nice exponential time bound for quantum algorithm, which is there are very few of them. So it is a nice result in the first place. And there are also some implications. For example, the bounded storage cryptographic schemes based on the hardness of parity learning is secure even against quantum adversaries. So we have also have these cryptographic implications if we have a negative answer. So now I have good news and bad news. The bad news is we didn't manage to prove either one of them. But the good news is, you see, now it is a time better than ever to try to push for either side of these problems, because whichever one you get, you win, right? So, so that's this win-win question that we proposed. What we actually proved is bound in the hybrid model. So what we proved, the statement of our result is that any quantum learning algorithm for parity learning that uses both classical memory and quantum memory requires either quadratic classical memory or linear amount of quantum memory or exponential time. So now you may ask, we defined the classical model and we defined the quantum models, but what is this hybrid model? What is the model that uses both classical and quantum memory? And that's a good question, and I'm going to answer that now. The answer is that we are still considering the quantum branching program. We are just putting restrictions on the quantum states and the quantum channels that you can apply. So we say a quantum state that has n-bit classical memory and qubit quantum memory is a state such that when you take its bilinear form on two quantum states that is labeled with different classical indices, the bilinear form must evaluate to 0. So it's much easier to understand if we're looking just at the density matrix. So we are restricting the density matrix to be block diagonal matrices, where the blocks there are n-bit classical memory, so there are 2 to the n blocks, and each block is a 2 to the q by 2 to the q positive semi-definite operator. And what we are really restricting is the quantum channels that you can apply. We limit them to be those ones that, when applied on matrices in this form, you must result in a matrix in this form. So the classical memory after the channel still needs to be classical. And so put it formally, those quantum channels must satisfy that for any such density matrix, what I said above still applies to the resulting density matrix. So that is basically model. And the takeaway message of our result is that if you are given a small linear amount of quantum memory, it does not help speeding up or reducing the large classical memory of a parity learning problem. And actually, our result does not only work for parity learning, it works for all the learning problems that are represented by something called extractors, which the classical lower bound for these problems are proved by Garg, Raz, and al. And I will come back to what is an extractor later on. So now is supposed to be the time for the proof of this result. But the truth is that this result is based on the the framework of the classical proof, the proof for the classical result, and and then you need to get it to work with all these quantum mechanics. So it gets really convoluted. I had a hard time writing it, and you will have a harder time trying to understand it in a very short amount of time. So I think that we are better off just to do something more enjoyable. Let's prove the much easier lower bound, where the lower bound is for linear quantum memory without the presence of classical memory. So we are going to show a proof that any quantum learning algorithm for parity learning using only quantum memory, it needs either a linear quantum space or it needs exponential time. So if you think about it a little bit, then it becomes trivial, because if you want to output X, you need to learn X. If you want to output X, you at least need n bits of quantum memory. Otherwise, you can't even output something n bit string long. But what we are actually going to show is that the bound works for even if you just want to output 1 bit information about X. So then it becomes not so trivial. The proof is actually a cute little proof. It's purely information theoretical and has nothing to do with our actual proof for the hybrid model. But at least you will get some idea of why information theoretical proofs will not work if you are shooting for a quadratic lower bound in space. Either it is quantum or classical. So the intuition is very simple. Is that a sample already needs like n+1 bits to store. So if you have a much smaller space, still linear, say epsilon n space, you cannot even store a sample, and the information you can store about X then is actually exponentially small. So in other words, we are going to prove that whatever happens, your quantum memory will depend very little on X. So to put it more formally, we examine the following measure on the dependence between X and the quantum memory, which is basically the smallest change that you can make if you change the quantum memory into something that is independent of X. So this is the formal definition, and we use this notation rho of xv to be the density matrix of the bipartite system of the unknown X, which is uniformly distributed, and the quantum memory V. Let's say at some point we are in this situation. So I use these rectangles to represent that those quantum memory states conditioned on a fixed input X, they are very similar to each other. So that means this measure psi is very small. And we want to know what happens if we hit each state with a random quantum channel that depends on the sample. Okay. So in other words, we want to show that the increment of this measure psi in each step is exponentially small. And to do that, because we are assuming that at the current step, these quantum memory states are very similar to each other. So why not just make them all the same? We are now assuming they are all the same, and then the inequality here becomes the second term in this inequality becomes 0, and the original inequality can be proved just by a triangular inequality and the fact that the quantum channels preserves trace norms. So now we need to introduce the concept of the quantum extractor. So what is an extractor? So first thing is that we are modeling these learning problems as matrices. We are this matrix is you can think of it as a function that has inputs on X and a random n-bit string A, so that the samples that I received in each step is in the form of A and the value of this matrix. Okay, and we say that this matrix is a strong quantum extractor with parameters Q and R if when you are given the full information of x, so here you for some random x, you know what x is, so you are fixing into say one column here, so you know the x, but you don't know the exact value of a, because if you know both x and a, you know the value of the matrix. Instead, what you are given is a quantum register of q qubits that depends only on a. So here I don't know how to visualize this, so I generated a random gradient, but that represents the given value of a quantum extractor. And when you are given both information, you still have no idea what is the value of this function. So put it formally, this value under the fixing of x and given the quantum register w, the value of this extractor should be 2 to the minus r, close to being uniform. And we know that parity learning is a strong quantum extractor with both parameters linear in n. And now the idea is that if we are given x and w, the value of the extractor is close to being uniform. It just means that the information of mutual information between the extractor and x and w should be exponentially small. And with some tricks in information theory, you can turn it into the fact that now basically it's saying that the value of the extractor and w is kind of almost independent of x. And the actual trick that we are using here is that now if at time t we are assuming the memory is independent of the value of x, the quantum register w that we are using is the combination of two quantum states. That is basically the result of the next of the quantum memory in the next step. If the sample that you received is a and 0, or if the sample that you receive is a and 1. So this, because you have very small quantum memory, so this w has like 2 times epsilon n space. So it satisfies well the requirement of the quantum extractor. And we notice that now the quantum memory in the next step can be decided entirely from this W register and the actual sample that the value of this extractor that you received. So we get what we wanted. And that's basically the entire proof. Okay. So I promised you about to talk about something about extractors. So we just showed that in that proof for the much easier result, we need something called quantum extractor. But what we actually proved for the hybrid bound is actually works for something called the two-source extractor, and it is a classical extractor. So the definition is basically the same, but it's actually more general. So we say that this matrix is extractor with 3 parameters k, l, and r. If you are given k-bit classical register depends only on x, and the l-bit classical register that depends only on a, the value of this extractor should be very close to uniform. And for a learning problem represented by such an extractor, what Gagan, Raz, and Tall actually proved is that you either need like k times l bits of classical memory, or you need many samples exponential in R. And what we proved here is that you need either k times l classical memory or linear in R quantum memory, or 2 to the order of R number of samples. Okay, so here's open problems. So first thing is that our conjecture that for parity learning, you either need quadratic quantum space or exponentially many samples. So the problem is, open problem is to prove or try to disprove that. And as I said, both cases win. And also you can try to improve the parameter in the quantum memory lower bound if you cannot prove just a quadratic bound, because possible lower bound for all these extractors in the parameters k and l are usually larger than r. So if you can prove something like you need either k times l classical memory or just a k plus l quantum memory, this will be an improvement for some problems like learning low degree polynomials. And finally, there's a problem of relation between classical and quantum extractors, because you see that quantum extractors very naturally appears when you are considering this type of problems. But what happens for our result for hybrid memory is that we proved it for more generally for classical extractors. So is it possible that every classical extractor is actually a quantum extractor, because quantum extractor is more restrictive? This problem is also kind of a win-win problem, but I think I don't have time to explain that, but just leave it as an open problem here. Yes, thank you.
Okay, are there any questions for Wei?
Thank you very much for the talk. I was wondering, so you're talking about memory and samples. Is there anything interesting to be said to also bring computation power into the game? Like trade-offs between memory, samples, computational power, something like this?
Good question. We didn't think about it, and I think it will get very complicated, and probably you can't prove unconditional results about them, because the computation powers, the bounds on the computational bound is very limited compared to this non-uniform most general model that we are considering here.
Okay, so the point is that what you have is unconditional, right?
Yeah, it's very hard to get. Possibly you can't get any unconditional bound from it.
Other questions?
Hi, thanks for the talk. I would like some technical clarification. So when you use a quantum extractor, what is your source and what is your seed?
Yeah.
I not quite follow.
So if you are familiar with the extractor, so this definition here, you see that the k-bit
the
classical register, that
okay.
just corresponds to like n minus k min entropy source, right? So this is why we call it two-source extractor. For quantum extractor, it's kind of hard to talk about min entropy, because now you have quantum memory for the side of this. And we say that it is a strong. Why we call it a strong extractor? Because one side of it, for X, you can just have the full information, right? And now for the other side, A, you have like a quantum memory for it. So I don't know how to phrase it.
So I guess my question is a bit more basic. So is X your source? For
you get
entropy source, or
as I said, it's hard to phrase it in the case of sources.
So there is no like source and a seed here.
Right. It is just like because of the alternative phrasing of extractor in the classical case, where you can just talk about remembering them with register instead of sources, and this definition like naturally extend to the quantum case. So I don't know if there's a equivalent definition using sources. Yeah.
Okay, last question, Quinten.
So is the difference between your quantum branching program and just sort of a quantum query model that you cannot query your information in superposition, or is there a reason why you didn't use it?
Good question. So here, this model is that all the samples that you received are classical. And so there's kind of like, so for learning problems, there's no queries. But if you think of an equivalent thing in query, you're still querying classical information. Yeah. You're just acting quantumly. Right?
Okay.
Okay, let's thank the speaker again.